Okay.
So let me show you the easy part first.
All right.
The easy part is, how do you predict the hybridization and what are the hybridizations? So that's the easy part. So we're going to talk about hybridization. So these are hybrid orbitals. And you know what hybrid dogs are, right? They're like half Chihuahua, half Dachshund or something like that.
Yeah, I got one right here.
Oh, really? Dachshund and Chihuahua?
No.
Okay.
But I know
Oh, they're back.
Okay.
So we will continue here and see how it goes with the mask on. Okay, so there are 5 types of hybridizations. And the 5 types are SP, SP2, SP3, SP3D, and SP3D2. Oh, there's 6. SP3D3. Oh, no, I'm sorry. Not the last one. So those are your types of hybridization.
Okay.
And here's how it looks around the central atom. That's an SP and that's an SP. This is an SP2. This is an SP2. And this is an SP2. So if this looks linear, it's supposed to. If this looks trigonal planar, it's supposed to.
Yeah, so I gathered that the electron geometry more or less determines that.
Not the electron geometry, the number of pairs.
Well, yeah, that's electron
So
geometry.
2 pairs, 3 pairs, 4 pairs, 5 pairs, and 6 pairs. This also informs the electron pair geometry, so that's why it's so easy. So without drawing the rest of these, what do you think this one is? It's tetrahedral, right?
Yeah.
And this one is trigonal planar or trigonal bipyramidal.
And then octahedral.
And octahedral. So that's the way the hybrid orbitals look. Now, as far as the molecular geometry goes, you still are going to use Vesper to name those, okay?
Okay.
So for instance, for octahedral, do you remember how we had octahedral, then we had square pyramidal,
Yeah.
then we had square planar?
Mm-hmm.
You still have that here.
Okay.
Now, the thing that complicates things is here and here you have what are called unhybridized p orbitals. And here you've only got 1 or 2, and here you've got 1.
Because there's 3 orbitals.
There's 3 p orbitals total, and 1 of them is being hybridized, and 2 of them are not. And here, 2 of them are being hybridized, and 1 is not.
Yeah.
So if we look at those 2 special situations and look at how the hybridized orbitals and the unhybridized orbitals look, for SP, That's an sp, and that's an sp. So this is interesting because that looks like a p orbital, doesn't it?
Mm-hmm.
But it's two sp hybrid orbitals.
Okay.
Now there's two p orbitals that we want to draw in here, and here's how they look. Here's one of the p's, and here's the other p. Now if I redraw this, it looks kind of like this. What I'm trying to do is draw this so that you can, whoops, I don't want to do that. So that you can kind of see the arrangement. It's kind of like X, Y, and Z.
Okay.
Okay. Now, how many orbitals do you see here that I'm pointing at? This whole figure, how many orbitals?
Is it 4?
4 orbitals.
Oh, tell.
An SP and an SP 180 degrees apart, a P and a P that are at right angles to the two SPs.
Okay.
And then when you look at SP2 plus an unhybridized P, one way to draw it is this way. And the unhybridized P is going to be perpendicular to all of this. So when you look at that, it looks complicated, doesn't it?
Mm-hmm.
There's a better way to draw it. What happens if I take my flat triangle like my hand and I look at it from the side like this? So I'm going to take the SP2s and draw them from the side, and it looks like this. Do you see how this one SP2 is kind of going back away from the center?
Yeah.
If we were to draw bonds, it would look like this. Okay?
Okay.
The reason I'm drawing it this way is it's a lot easier to see where the P goes.
So up and down.
Yeah. So in essence, the P goes in the space that's left over where it will have the least repulsion with the other orbitals.
The unhybridized P.
I'm going to pause this for a moment.
Okay.
Actually, I'm just going to make them be on the Zoom video.
Yeah. This is what his new stove looks like.
Should have moved stuff inside here a little more. I moved the cars out of the way. It would have been heck to
No, this is all fine.
get past the cars.
Appreciate it.
Ooh, it's wider than the other, I think.
For now.
Would fit in there.
Oh yeah. I can measure it.
Okay, cool. Thanks, guys. I'm going to go back to this. Try not to be bored. Okay, so do you understand the relationship here?
Yeah. What was the most confusing part to me was when we're putting together, like when we're writing out the electron configuration. And then
There's no electron configuration for this. That's a molecular orbital theory.
so in the book, I'm looking at like examples that let me see. Like for beryllium, it draws like the 2s and then the 2p, and how they combine together, I guess, is what it's trying to show.
Okay, but that's not an electron configuration. It's just how the orbitals hybridize. So essentially, if you look at something that does the SP hybridization,
Mhm.
this is a way to think about it. You've got an s orbital. You've got 3 p orbitals.
Yeah, that's what I'm talking about.
So when you combine them together and combine just an S and a P, when you hybridize them, the energy will be, let's say, halfway between the S and the P.
Yeah.
So that's an sp hybrid orbital, and that's an sp hybrid orbital. When you hybridize two, you get two.
Okay.
And you put down the orbitals that you hybridized. So these are left behind. So I'm going to put them off kind of like this, where they were originally. They're
Yeah.
still there.
Okay.
So when we draw this, here's an SP. Here's an SP. Here's one of the P's. And here's the other P. So that's what's going on.
Okay.
And when you take an S and three P's and you hybridize these three, you're going to get this. One of your P's is left over. Same, should be about the same level, right?
Yeah.
And these are called SPP because you're hybridizing one S and two P's. Now we don't write it this way. How do we write it?
SP2.
SP2.
Okay. So if
That's the reason why we say SP2. Now, when we arrange these, I think this is the most instructive way to draw them so you can see their orientation relative to one another. Is this helpful?
yeah,
Okay, so do you want to see what happens when we do all four?
sure.
So when we do all four, so I'm going to circle all of them. What happens is you get four orbitals, and this one's going to be SPPP, right? But what do we call that?
SP3.
SP3. So what's the best way to arrange four SP3 orbitals of equal energy?
Tetrahedral.
Right.
Okay.
And then what about the next one? So you have an S, a P, a P, a P, a D, a D, a D, a D, a D, and we're going to hybridize these. So you'll notice whenever you hybridize, what do you hybridize first? Those most stable orbitals.
Okay.
So these five are going to look like this. Where each is SP3D. Now, notice I'm not drawing the D's in. Do you know why?
Too hard?
They don't really participate in bonding.
Oh.
So only the hybridized D does.
Right.
And it only does so as part of a hybridized orbital.
Okay.
So what do you think the next level would look like?
Just another D.
Now, the only elements that can do this type of hybridization are those in the third, fourth, fifth, and sixth and seventh periods. And the reason for that is because in period 2, there are no d orbitals.
Right.
So if you don't have d orbitals, you can't have sp3d or sp3d2.
Okay.
So what are 6 of these going to look like?
SP3D2.
I kind of call this the dragonfly, right?
Oh, okay, yeah.
It also looks like a jack from that game with the ball and the jack.
Mm-hmm.
So how do you tell the hybridization of an atom? And it's really simple. You just look at the Lewis structure, ask how many pairs, and that tells you the hybridization. And if you want to know how many pairs to look for each of these, if you want to know how many pairs to look for, it's real simple. How many orbitals do you see? Well, I see one s and one p, that's 2. One s and 2 p's, that's 3. One s and 3 p's, that's 4. So the hybridization tells you how many pairs you're looking for if you count the superscripts. Now, what's the superscript if you don't write it?
1.
It's 1. So we can look at all sorts of molecules that we've seen before and decide the hybridization. So if you had this, how many pairs?
4.
And sometimes I get to the hybridization this way, 4 pairs, right?
Mm-hmm.
So out of all the orbitals, which is the most stable, S, P, or D?
S.
S. So there's one of them. And then the P's, right? But how many P's do we have?
3,
3, right?
I guess.
So here I have my 4 pairs, right?
Right.
So sp3 hybrid. And
So
sp3 hybridized is going to look like this. Tetrahedral. See how easy that is? So since you have to leave by 11, I'm going to get to a really complicated one right now. Not that complicated, but complicated. There is a molecule that is this. It's called ethene. It's also called, what else do they call it? Some people call it ethylene. But ethene is the name I would rather have you know. And the Lewis structure looks like this. And we could use VSEPR and figure out the molecular geometry, right?
yeah.
If we use VSEPR, we would get this. Because each of these has 3 pairs, which means trigonal planar, right?
Yeah.
Or you could get this. Because isn't that trigonal planar?
Yeah.
Isn't that trigonal planar?
Mm-hmm.
So we could get either of these, or we could get any angle we wanted, right?
Right.
So let's see what happens when we use hybridization, okay? So when we use hybridization, this is what we get. This guy is sp2, and this guy's sp2.
And it's only for the central atom, right?
Right.
So
Hybridization applies atom by atom by atom.
do we consider the double bond between the 2 carbons?
We're going to see how we deal with the double bond here in just a moment.
Okay.
Now, I'm going to purposefully draw this a certain way. Hang on a second. Let's see here. More. Okay, so each of these is sp2 hybridized, and I could draw it this way. Right? But I want to draw this way. because I want to show you how all of the bonding occurs, okay?
Okay.
Now, these are sp hybridized. This is just a 1s orbital. There's no hybridization when you only have one orbital.
Yeah.
I mean, why would you do that, right?
Right.
So let's look at this carbon here first. It's going to look like this. And I'm going to go ahead and write sp2, sp2, and sp2. See how clever I am? You can't even see the whole P here because it's tucked behind the other one.
Okay.
Now, where's the P orbital?
Is it up and down?
That's right. And that's why I drew it this way, because it's really easy to see. Now, valence bond theory says that to make a bond, orbitals have to overlap.
Yeah.
So here is a hydrogen orbital, a 1s orbital, overlapping with a carbon sp2 hybrid orbital. And this is a bond right here. And so normally you put 2 electrons in there.
Okay.
So that's happening up above too. You've got a hydrogen atom and 2 electrons in there.
Yeah.
What's happening with the other carbon? Well, with the other carbon, we're going to do this. And here you have an sp2 overlapping with an sp2.
Okay.
And I'm going to redraw this very quickly. So this is from the Lewis structure. Where this is sp2, this is sp2, this is sp 1s, 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 1s. So here's one of my carbons with an sp2 overlapping with another sp2 from another carbon. And that's kind of where I left off on the other drawing.
Mm-hmm.
But right now I'm going to go ahead and put in the other stuff. And here's my P. So that's where we left off. Now for this, how do I draw the rest of the carbon? And the answer is kind of like the mirror image of this one, which means so they're both triangles, right? Flat triangles where they're, if you look at them from the top, they're kind of doing this. Where here's one carbon, hydrogen here, hydrogen here, hydrogen here. That's looking from the top.
Okay.
Okay. So we see one of the bonds between the 2 carbons, right?
Yeah.
And here's the bonds to the hydrogens.
Okay.
What's neat about this is it shows us the origin of the second bond. What happens here is that these 2 p orbitals are close enough together that they actually bond. You have to imagine this. There's something called the space filling model for drawing molecules. And when you draw this molecule using the space filling model, you do this: carbon, carbon, hydrogen, 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 hydrogen. So can you see that that's a double bond there?
I guess.
I can't. All I see is 2 atoms touching.
Okay.
So I know there's a bond. I don't know if it's a single, double, or triple.
Yeah.
There's a bond there. I don't know if it's a single, double, or triple. If you tell me that's a hydrogen, then I know it's a single. Why do I know it's a single?
Because hydrogen can only have one bond.
Exactly. Okay. And here, if I tell you these are carbons, then I know what type of bond this is. If this carbon is making a single bond to that, and this carbon is making a single bond to that, that's only 2 bonds. How many bonds does carbon need?
4.
4. So there's a double bond there.
Right.
One of those bonds is from an sp2 hybrid overlapping with another sp2 hybrid.
Okay.
So these p orbitals, you got to imagine, they're right here on top of the carbons and they touch. The way I've drawn them here, they don't touch, do they?
Mhm.
So here's what I do to make them touch. I say, oh, they touch. So these 2 orbitals that are doing a side-by-side overlap, how many electrons are in there? Well, let's take a look. How many electrons in this overlap?
4.
How many electrons in this overlap that I'm pointing at?
Well, it's a double bond.
No, right here. How many electrons? They're drawn.
Oh, just the 2.
How many here?
2.
How many here?
2.
How many here?
2.
How many here?
2.
How many electrons in an overlap?
2.
How many in this overlap?
Well,
2.
2.
Why would you change it? So there's my 2.
I don't know.
Where are these 2 electrons? They're somewhere in this circle. Now, let me show you that the book with its molecular modeling programs can draw something better. Are you ready to look at that?
Yeah, I've been looking at it.
You are looking at it.
Yeah.
So let's take a look at the similarities. What page are you on when you're looking at this?
Right now, 422.
So when I'm in page 700, I'm too far.
Yeah.
All right, so can you see that this drawing here is the same as this drawing here, but this one's on its side and this one is looking from up above.
Mm-hmm.
So when they take this and they rotate it 90 degrees, this is what you're looking at. And you see this blue balloon on top and this blue balloon on the bottom?
That's the p orbitals?
That's the 2 p orbitals overlapping. And this is how I draw it because I can't draw balloons. I don't want to bother.
Oh.
This is less crowded than if I draw balloons.
And is that when we get to talking about pi or sigma?
Yeah, this is a sigma bond. 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 And this is a sigma bond. This is a pi bond. And if you take a look at the nucleus of the atoms, here's the nucleus and here's the nucleus. Sigma bonds are when the electrons are directly between the 2 nuclei.
Yeah.
Now, here's the nucleus of this carbon atom. Here's the nucleus of this carbon atom. Are these electrons directly between the 2 nuclei? It's a pi bond. And when you're looking at a Lewis structure, it's real easy to see pi bonds. So
Okay.
let's say you have this. So I'm going to give you a second to draw that. And we're going to do 2 things here. We're going to pick the hybridization of every atom.
Okay.
And then we're going to count how many sigma bonds and how many pi bonds.
Okay.
So have you drawn it yet? Great. How about this carbon atom? What's the hybridization?
It's tetra, so sp3.
sp3. How about this carbon atom?
Trigonal, so sp2.
How about this one?
Is it just SP?
That's right. How about this one?
SP.
SP, because it has two pair.
Yeah.
One pair is the triple bond, one's the double bond, or one's the two electrons.
Yeah.
How about this oxygen?
Trigonal, so SP2.
Okay. How many sigma bonds total?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5. Because we saw in the previous example that when you have a double bond, one's a sigma, one's a pi, right?
Oh yeah.
So 1, 2, 3, 4, 5, 6. What about triple bonds? Well, one's a sigma, the other two are pi's.
Okay.
So 1, 2, 3, 4, 5, 6, 7. 7 sigma bonds. How many pi bonds? 3 pi bonds. Because when you have a single bond, that's a sigma. When you have a double bond, it's a sigma plus a pi. And when you have a triple bond, it's a sigma plus 2 pi's.
Okay.
So it's real easy to count sigma bonds and pi bonds, agreed?
Yeah.
Now let's try and draw this. So I'm just going to show you the drawing. We're going to start off with this carbon here. What I'm drawing now is I'm drawing the carbon that's sp2 hybridized.
SP2. Okay.
Okay. So actually, this one is tough to draw, showing all the bonds. So I'm going to draw it first just in 3D.
Are we going to be needing to know how to draw these?
You
Super fun.
definitely need to know how to draw that.
The one we just did?
Yeah. And other ones like this with double bonds in it. Usually I don't make you do triple bonds because they're boring.
Okay.
Like if you do this one, it's just this. SP, 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 hydrogen, SP, hydrogen. And then you've got this, which is one of the pi bonds. And you got this, which is another pi bond. Okay.
So we have pi bonds if they're unhybridized p or p's, right?
That's the only way to get pi bonds, with unhybridized p orbitals.
Okay.
Okay. So back to this guy. I guess I just want to draw it three-dimensionally, and it would look like this. So does that carbon look tetrahedral?
Yeah.
Does that one look trigonoplanar?
Mm-hmm.
Does that one look linear?
Mm-hmm.
That's why these triple bonds come straight off of the single bond in the same line.
Yeah.
You can't do this. That would be wrong, right?
I guess.
Well, how many pair are on that carbon?
2.
So what's the arrangement of the pairs?
Linear.
Is that linear?
I see.
So
No.
we can't do that. That's not the way it should be drawn.
Yeah.
So that's why this looks straight, because that carbon's linear. And that's why you put these lone pair over here instead of on top or the bottom, is because you want to make it look linear, right?
Yeah.
The only thing that we could do to improve this is the following. Now, the way I put the lone pair on that oxygen, does it look trigonal planar?
Mm. Well, I mean, I guess it kind of does.
It does. If I do this, does that look trigonal planar?
Yeah.
No, this,
Oh,
because that's 180 degrees, right?
yeah.
Now, so that's why a lot of these drawings, you see the dots kind of a kilter,
Uh-huh.
because it's showing the orientation. And this is in an sp2 hybrid orbital. This is in an sp2. This is an sp2. Plus, what else is happening here?
The unhybridized piece.
From oxygen and the unhybridized P from carbon are bonding.
Mm-hmm.
So it turns out, remember when I drew this? Where did that go? I'll find it here in a bit. Ah, here it is. Do you remember when I drew this? I said, is it this or this?
Mm-hmm.
That's a check. That's a big no. Why is that a big no? And I'm going to show you why now. Here, this has a p orbital that's like that, right? Where's the p orbital on this guy? Well, it's going in and out of the plane of the board. Are these p orbitals in any position to actually go side by side and overlap? They're not. But this has a p orbital here, and this has a p orbital here. Can they do the side by side overlap?
Okay, because they're parallel to each
They're
other.
parallel. If they're not parallel, they can't bond. So guess what that means for this molecule? It can't twist.
Okay.
You have to do special reactions to this to make it twist.
Okay.
And that leads to a type of geometric isomerism that's possible. So here we have two molecules that are similar to the one we just looked at.
Mm-hmm.
And so you see this is pretty flat, right?
Yeah.
And that's the actual geometry. Is this polar?
Yeah.
Where would I draw the arrow next to it?
Going down.
Going down.
Going. Yeah.
Is this one polar?
No. I don't think so.
And they can't turn into the other one without doing chemistry on them. So you can have a jar of this and you can have a jar of this.
Okay.
Now, this is what they call cis, and this is what they call trans.
I was wondering about that in the book. It didn't really.
And to decide whether you have cis or trans is you kind of draw a line through the molecule that is parallel to the double bond. So do you see how I've drawn a line through the molecule parallel to the double bond?
Yeah.
If the two hydrogens are on the same side, of a line, then it's cis. And that's the way I remember it. Cis, same side.
So does it have to do with polarity, or is it hydrogen specific?
Well, it can affect polarity, but here, do you see how the two hydrogens are on opposite sides?
Mhm.
That's called trans. And the way to remember that is because of the Transcontinental Railroad. You ever heard of that?
Yeah.
It goes across the nation from side to side. And here's your continental divide right there.
Yeah.
Goes from East Coast to West Coast. And do you know where they met when they were building that? In
No.
Utah. About 20 minutes from where my sister lives.
Oh.
So yeah, that will affect polarity. You know, cis is more likely to be polar than is trans.
But it's not always, or
Not always, no. Now, what if you have something like this? Is this polar?
Mm. Yeah.
Yeah, definitely. I'd do this for this one, right?
Yeah.
Okay, this one's polar. Is it cis or trans?
Cis.
If you look at these two hydrogens, you'd say, oh, it's cis. If you look at these two, it's trans, right?
Yeah.
It's neither.
Okay.
To have cis or trans, you have to have exactly two hydrogens. Two, no more.
Okay.
Now, how about this one? Is this polar?
Yeah.
Most definitely, right?
Mhm.
Is this one cis or trans? Not cis, not trans.
So the divide has to be a horizontal one?
So, well, yeah, the divide has to be a horizontal one. So it looks like trans, doesn't it? Because they're on opposite sides.
Oh, yeah.
But now you just learned the next lesson is not only do you have to have exactly two hydrogens, but one has to be bonded to one carbon and one bonded to the other. They can't be both bonded to the same carbon.
Okay.
Because the idea here is for cis and trans, you can turn one into the other if you draw a bond like that and you just switch two of these. If I switch this hydrogen and fluorine, I'd make this, right?
Yeah.
If I switch this fluorine and fluorine, would I make a different molecule?
No.
If I switch this fluorine and this hydrogen, would I make a different molecule?
Yeah.
No. And let me prove it to you. Do you see this molecule here where the fluorine is at the bottom?
I see. Yeah.
And if I switch this, the fluorine would be at the top, right?
Right.
And so here, do you see the fluorine at the top here? Basically, you can see through this and you can see the fluorine. So here's the fluorine at the top, right?
Yeah.
What happens when I switch it like that? The fluorine's at the bottom. It's the same molecule. The reason we get to move things around like that is because this is not about resonance. Resonance, you're not allowed to do that, but here we are. So it's the same molecule. Let me see if I can kind of show you that another way. So here, if I switch this fluorine and this hydrogen, the fluorine would be on the bottom, right?
Yeah.
But let's look at this molecule from the opposite side. You see how the fluorine's on the bottom?
Yeah.
So if I switch these two, I don't get a new molecule. I just get the same molecule, but looking at it from the backside.
Right. Okay.
So what did you learn about cis and trans? What are the things that you need for cis and trans? What have we just learned? You need what? Carbon-carbon double bond, right?
Yeah.
You need 2 hydrogens. And what else? 1 hydrogen to each carbon.
So the hydrogen has to be bonded with the carbon.
Yeah, so it has to be exactly 2 hydrogens. And here, it doesn't matter what the rest of this is. I mean, this could be a fluorine. This could be a chlorine. It's still cis. And this could be a bromine. And this could be an iodine. It's still trans. What makes it cis is the hydrogens, not the others.
On the, okay.
So do you see how we have a carbon-carbon double bond?
Yeah.
Do you see how we have 2 hydrogens?
Mm-hmm.
Do you see how 1 hydrogen to each carbon is what we have here?
Yeah.
And the same here. So here, you want some homework?
Sure.
Here's the Lewis structure. Nope, this is not what I want. Sorry. Start over. Can you draw that in 3D?
Maybe. Yeah.
Give it a shot. And I'm going to put you on pause because this is going to take you until your 11 o'clock time. Try and draw it in 3D based on what we just learned.
Okay. The first carbon is trigonal planar, so it's sp2, so 3 sp2 bonds.
Okay, so we've got sp2.
Yeah.
How about the second carbon? Or middle one, if you want to call it that.
sp, so it's linear.
sp. How about the last carbon?
sp2.
sp2. Now, I already showed you the best way for drawing a double bond is with the triangle sideways, right?
Yeah.
So you should do this for that carbon on the left end.
Yeah. About as far as I got.
Okay. Draw the hydrogens in.
Okay. They're just little bubbles, kind of, right?
Circles, yeah. Spheres, really, but
Yeah.
okay, there's the 2 hydrogens. How about this carbon in the middle? What are you going to draw?
Well, it overlaps with that SP2.
Well, first of all, it's sp hybridized. How would you draw that?
I don't know.
How many orbitals are there? How many hybrids?
2.
Okay, so what's the best way to draw two orbitals as far
Oh.
apart from one another as possible?
Linear.
So like that?
Yeah.
Okay.
And then those are
Where,
S
where are the P's?
perpendicular to the SPs
Okay, there's one. Where's the other one?
on the bottom. Oh, like on the Z axis?
Okay, so we're gonna have to draw it like this. So how are we forming this pi bond here?
Um, with the p orbitals
That are on what axis?
on the same axis.
So we're gonna call that the y-axis.
Right.
Okay, great.
And then
Now, how are you gonna draw that last carbon?
Oh, it's going to be trigonal.
So like this, just like the other one on the right or
Yeah.
left?
Yeah,
Okay, cool.
I think.
Where's the p orbital?
Up and down.
Where's the pi bond?
Does it bond with the center carbon p orbitals
The one that's vertical?
on the Y?
No, can't do that. This guy's already bonding. He can't bond again.
Okay.
No one's bonding with this p orbital.
But it's
But
different.
but they're perpendicular.
Okay. Yeah.
So maybe we draw it this way.
That's why you switched to pencil.
You should have known something was up. So maybe we draw it this way. Is this still trigonal planar
So
for the sp2 hybrid orbitals? Does that look trigonal planar pretty much?
yeah.
With a hydrogen here and a hydrogen here?
Yeah.
Okay, so here's the unhybridized P, right?
Right.
And
Okay.
there is your other pi bond. So if we draw this in 3D, what's it going to look like? It's going to look like this. Do you see that for that?
Yeah.
And then that, right? Because even though the pi bond is above the plane, you don't see the electrons that way.
Okay.
So this is what you see. It's twisted, right?
Yeah.
It's not this at all. It's twisted.
Yeah.
Kind of interesting. What do you think would happen if we had another one in there?
It'd have to be twisted on the
It'd
axis.
be twisted again, wouldn't it?
Yeah.
And then it'd end up being flat.
Right.
And then if we put 4 double bonds, it'll be twisted again. So it's like 1 double bond, it's flat. 2 double bonds, it's twisted. 3 double bonds, it's flat. 4 double bonds, it's twisted. It's 10:59, so maybe we better call it quits so that you can do your thing.
Okay. Alrighty, thank you.
All right. Good job.
Bye.
Bye-bye.